Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel. In this video, we are going to study about angle of minimum deviation, refractive index of the material of the prism, dispersion of white light through prism, the angle of deviation, dispersive power, and scattering of sunlight.
Angle of minimum deviation. A graph which is plotted between the angle of incidence and angle of deviation is shown in this figure 6.41. Along the x-axis, angle of incidence I1 is taken, and along the y-axis, angle of deviation D is taken. And from this graph, you can see that as the angle of incidence increases, at first angle of deviation decreases. And at one point of angle of incidence, the angle of deviation is minimum, and as the angle of incidence is further increased, angle of deviation increases. So here as the angle of deviation decreases with increase in angle of incidence, and it reaches a minimum value D, and then it continues to increase. This minimum value of angle of deviation is called angle of minimum deviation D. And at minimum deviation position, we should consider 3 points. The first one is the angle of incidence I1 is equal to the angle of emergence I2. Then the angle of refraction at the phase 1 and phase 2 are equal. That means R1 will be equal to R2. So here this prism is kept at an angle of minimum deviation. Then the third one is the refracted ray inside the prism is parallel to the base of the prism. So like this. So here the refracted ray is parallel to the base of the prism. So that is what shown in this figure 6.42. Then we will consider about the refractive index of material of the prism. How to find out the refractive index of the prism? By knowing the angle of minimum deviation. And at minimum deviation we know that I1 is equal to I2 equal to I, and the angle of refraction R1 is equal to R2 equal to R. Therefore the equation 6.88 can be written as D equal to I1 plus I2 minus A. That means 2I minus A. Therefore angle of incidence I is given by A plus D by 2, where A is angle of the prism, and for an equilateral prism this A will be equal to 60 degrees. Then the equation 6.87 can be written as R1 plus R2 equal to A. That means 2R equal to A. Therefore R, the angle of refraction, is given by A by 2, that is half of the angle of the prism. So substituting values of I and R in Snell's law, n is equal to sin I by sin R, we can write the expression for the refractive index of the prism as n is equal to sin A plus D by 2 by sin A by 2. So this equation is used to determine the refractive index of the material of the prism. These angles A, that is the angle of the prism, and angle of minimum deviation can be measured experimentally. Next we will study about the dispersion of white light through a prism. The angle of deviation produced by a prism is so far discussed only for monochromatic light. What is a monochromatic light? That is light of single color. When white light enters into a prism, an effect called dispersion takes place. What is dispersion? How to define it? Dispersion is spreading of white light into its constituent colors. This band of colors of light is called its spectrum. So what is a spectrum? That is nothing but a band of colors of light, in the case of visible light. When a narrow beam of parallel rays of white light is incident on a prism and the refracted beam is received on a white screen, a band of colors is obtained in the order given by the word Vibgea. Here these letters stand for the colors like violet, indigo, blue, green, yellow, orange and red. Violet color is the most deviated one and the red color is the least deviated, as shown in this diagram. So here, when you pass white light through a prism, you will get a band of colors called as a spectrum, in which violet is most deviated color and red color is the least deviated. The colors obtained in a spectrum depend on the nature of the light source. Each color in vacuum has a definite wavelength, and the red color has the longest wavelength of 700 nanometer, while the violet color will have a shortest wavelength of only 400 nanometer in vacuum. And though all the colors have different wavelengths, they will all travel with the same speed in vacuum. The speed of light is independent of wavelength in vacuum. Therefore, vacuum is a non-dispersive medium. And this is Isaac Newton's experiment on prisms. He has demonstrated through a classic experiment to produce white light by recombining all the colors of Euclid. He used a prism to produce dispersion and made all the colors to incident on another inverted prism to combine all the colors to get white light, as shown. But when white light enters a medium, red color will travel with highest speed, violet color will travel with least speed. Hence, the wavelengths of colors in a medium are no longer the same as they are in vacuum. Actually, the dispersion takes place in a medium because of the difference in speed for different colors in a medium. In other words, the refractive index of the material of the prism is different for different colors. For violet color, the refractive index is the highest, and for red color, the refractive index is the least. So you should remember that for violet color, the refractive index is maximum, and for red color, the refractive index is minimum. The refractive index of two different glasses for different colors is shown in this tabular column. So this tabular column gives the refractive indices for different wavelengths in vacuum in two different types of glasses. For violet color, the wavelength in vacuum is only about 396.9 nanometer, and for crown glass the refractive index is 1.533, and for print glass it's 1.663. These are the values for these different colors. Now we will study about the dispersive power. For this, let us consider a beam of white light passing through a prism, and it gets dispersed into its constituent colors as shown in this diagram. If the angle of the prism is small, of the order of only 10 degrees, the prism is said to be a small angle prism. When the rays of light pass through such prisms, the angle of minimum deviation also becomes very small. Let A be the angle of the small angle prism and delta be its angle of minimum deviation. Then the equation 6.89 can be written as n equal to sin A plus delta by 2 by sin A by 2. And for small angles of A and delta, as this A will be only about 10 degrees and delta the angle of minimum deviation, the equation can be written as delta, that is the angle of minimum deviation, is given by n minus 1 into A, where A is the angle of the prism. So when white light enters the prism, the deviation is different for different colors. Thus the refractive index is also different for different colors. If delta V and delta R are the angles of minimum deviation for violet and red colors respectively, then NV and NB the refractive indices for the violet and red color respectively. Then for violet color, the angle of minimum deviation delta V is given by NV minus 1 into A. And for red color, is given by delta R equal to NR minus 1 into A. Thus the angle of minimum deviation for violet color delta V is greater than the angle of minimum deviation for the red color delta R. The refractive index for violet color NV is greater than the refractive index for red color NR. So subtracting this delta R from delta V, we will get this expression as delta V minus delta R equal to NV minus NR into A. This angular separation between the two extreme colors, violet and red, in the spectrum delta V minus delta R is called the angular dispersion. If you take delta as the angle of minimum deviation for any mean color such as green or yellow and the n corresponding refractive index, then delta can be written as n minus 1 into A. The dispersive power omega is defined as ratio of the angular dispersion for the extreme colors to the deviation for any middle color. So the dispersive power is the ability of the material of the prism to produce dispersion. So omega can be written as angular dispersion by the middle deviation. That's given by delta V minus delta R by delta. So substituting for delta V minus delta R and delta, this expression omega equal to NV minus NR by N minus 1. So the dispersive power is a dimensionless and unitless quantity, and the dispersive power is always positive. The dispersive power of a prism will depend only on the nature of the material of the prism, and it is independent of the angle of the prism. Now let us study about the scattering of light, the last topic in this chapter. When sunlight enters the atmosphere of the Earth, the particles present in the atmosphere change the direction of the light, and this process is known as scattering of light. If the scattering of light is by atoms and molecules which have a size very much size A, which is very much less than that of the wavelength lambda of light, then A is very much less than lambda. The scattering is called Rayleigh scattering. The intensity of light scattered in Rayleigh scattering is inversely proportional to the fourth power of its wavelength. So I is directly proportional to 1 by lambda power 4. So according to this equation, during daytime, violet color which has the shortest wavelength will get more scattered than the other colors. The next scattered color is blue. As our eyes are more sensitive to blue color than violet color, the sky will appear blue during daytime. That is as shown in 6.4b here. But during sunrise and sunset, the light from sun travels a greater distance through the atmosphere. Hence, blue light, which will have a shorter wavelength, is scattered away, and the red light, which has a longer wavelength, only will reach our eyes. And that is because of less scattering. This is the reason for the reddish appearance of sky during sunrise and sunset. And if light is scattered by large particles like dust and water droplets present in the atmosphere, which have size A greater than the wavelength lambda of light, A will be very much greater than lambda. The intensity of scattering is equal for all the colors, and this is called non-Rayleigh scattering, and it is independent of the wavelength. And it happens in clouds which contains a large amount of dust and water droplets, like this. Thus in clouds, all the colors will get equally scattered, and that's the reason for the whitish appearance of cloud, as shown in this diagram. But the rain clouds will appear dark. That is because of the condensation of water droplets on the dust particles, which will make the clouds opaque. And if the Earth has no atmosphere, there would not have been any scattering, and the sky would appear dark. That's why the sky appears dark for the astronauts who could see the sky from above the atmosphere.
Hey, welcome to this explainer. Ready to dive into the hidden physics inside a simple glass prism? Ever wonder how plain glass creates rainbows? Well, it's all about bending light, and honestly, it's incredible. We call this dispersion. It's literally just ordinary white light splitting into the whole visible color spectrum. As light enters, its deviation drops to a very specific minimum point, then goes right back up. At that exact minimum point, boom, perfect geometric symmetry suddenly emerges right inside the prism's light path. Because of this symmetry, the math totally simplifies for all the angles involved. It's super elegant. So how do we actually use this minimum deviation to figure out the glass's unique properties? We just need two things, A for the prism's angle and D for that minimum deviation. Just pop those variables right into Snell's law to find N, the material's refractive index. Easy. Let's try it out. Picture an equilateral prism with a 37-degree angle of minimum deviation. We just crunched the numbers, the sine of 48.5 divided by the sine of 30. And there we go. We get a refractive index of exactly 1.5 for this glass. But hold on, why does this bending create that beautiful, full-color spectrum we all know? Well, a material's refractive index actually shifts depending on the specific wavelength of the light hitting it. So violet light slows way down and bends the most, while red light bends the least. The math confirms it. Refractive indices really do shift across different wavelengths for various glass types. It's wild. different materials like flint versus crown glass bend the exact same colors in totally different ways. Makes you wonder, right? How does this light-bending physics dictate how your own eyes perceive reality?